BJTs are active electronic devices. By their very nature, they are non-linear. Their behavior can be converted from non-linearity to linearity with the help of equivalent circuits. When it is linear, one will be able to use the ordinary circuit laws like Ohm's law, Kirchhoff's law, and such other laws for the analysis of a transistor amplifier. Several equivalent circuits are there. H parameter equivalent circuit is most popular one, widely used one. The circuit involves 4 parameters: Hi, HR, HF, and H0. These 4 parameters are dimensionally different, and hence they are called hybrid parameters or H parameters in short. Information pertaining to these parameters are provided by the manufacturers in the data sheets that come along the transistors, BJTs. Electronic devices, BJT equivalent circuits, part 1, series on semiconductor devices and circuits, lecture number 5.10. BJTs, bipolar junction transistors, are electronic devices. By nature, they are non-linear devices. Equivalent circuit of a BJT is a linear circuit, and this circuit represents the BJT in that its behavior is, electrical behavior is somewhat similar to the behavior of actual device BJT. Equivalent circuits are required and useful in analyzing circuits in which BJT is there. Several types of equivalent circuits are available. Some are small signal equivalent circuits, some are large signal equivalent circuits, some are low frequency equivalent circuits, some are high frequency equivalent circuits, some are H parameter circuits, some are T equivalent circuits, some are pi equivalent circuits. Several different types are available for BJTs. In the present session, we consider H parameter equivalent circuits of BJT. Let us start the session by introducing H parameters. H stands for hybrid. There are 4 parameters in the equivalent circuit of BJT. These 4 parameters have different dimensions or units. That's why they are called hybrid parameter. A few points regarding hybrid parameters. The names and units of parameters are given here. HI. HI actually represents input resistance with the output short circuit. HR represents a reverse open circuit voltage amplification. It is a dimensionless quantity. Notice this is a reverse open circuit voltage gain. Amplification means output by input. Voltage amplification means output voltage by input voltage. Reverse voltage amplification means input voltage by output voltage. HF is a negative forward short circuit current gain. It is basically current gain. It is dimensionless quantity. H naught is output conductance with the input open circuited. It is measured in mhos. Notice HI is in ohms, H naught is in mhos, HR, HF. HR is reverse voltage gain, HF is forward current gain. These are all different dimensions quantities. A letter is added as another subscript to these parameters to indicate a transistor configuration. E for CE, B for CB, C for CC. For example, HIC means input resistance with output short circuit in case of CC configuration. If E is there in place of C, then it represents input resistance with output short circuit in case of common emitter configuration. Similarly, CB. Here are shown the defining relations. HIE, HRE, HFE, HOE. See, E is there in the subscripts. So it implies that these parameters pertain to common emitter configuration. In the second column, HIB, HRB, HFB, HOB are there. So these parameters represent values pertaining to CB configuration. In the third column, HIC, HRC, HFC, HOC. HIC is input resistance, HRC is reverse voltage gain, HFC is forward current gain, HOC is conductance. For common collector configuration, actual definitions are given here for all the three configurations. Here is shown H parameter equivalent circuit of common collector configuration. In A is shown actual circuit, common collector circuit. Collector is common. This is common. Collector is common for input and output common collector configuration. Now its equivalent circuit is shown here. It consists of one resistance, one conductance, one voltage source, one current source. Voltage source and current source both are dependent sources. Here is shown H parameter equivalent circuit of CA configuration. Emitter is common. So it is common emitter configuration. Emitter is common. In B is shown the equivalent circuit. Here also one can see one resistance, one conductance, resistance on the input side, conductance on the output side, one voltage source, dependent voltage source, HREVC, one dependent current source, HFE. The current output of current source depends upon IB, input current. The voltage output of the voltage source, dependent voltage source, it depends upon VC, output voltage. So dependent voltage. Here also, like previous case, two sources, one resistance, one conductance is there in the circuit. Of course, it is HIE, it is HRE, it is HOE, it is HFE, as this configuration is CE. Now we consider H parameter equivalent circuit of CB. S is common, that's why it is CB configuration. In B is shown equivalent circuit. Here also one can find a resistance HIB, a conductance H0B, a voltage source, dependent voltage source HRBVC, a dependent current source HFBIB. The output voltage depends upon output voltage of the dependent voltage source. It depends upon output voltage VC. Similarly, the current output of the dependent current source HFEIB, it depends upon input current. The source output on the output side depends upon the input current. The source on the input side voltage depends upon output side voltage. Some more points regarding H parameters. Equivalent circuit of BJT in any configuration in terms of H parameters consists of an input Thevenin equivalent circuit and an output Norton's equivalent circuit. The Thevenin circuit consists of a resistor and a dependent voltage source. We have seen in all the three cases it is so. In series, this voltage source actually represents the signal feedback from output to input, which is considered as harmful for stability of the amplifier. The output of the source depends upon the output voltage of the transistor. So some feedback is built into the equivalent circuit, which leads to instability, harmful. The output Norton circuit, on the other hand, consists of a dependent current source representing the gain of the transistor and a conductance in parallel, H naught. Typical values of H parameters are given. One point to be noted here is HI is not the same for three configurations. HI for C is not equal to HI for CC. It is different from HI for CB. HR also different for different configurations. So HI value is 1.1 K for CE, 1.1 K for CC, 21.6 ohms for CB. HR is 2.5 into 10 power minus 4 for CE, 1 for CC, 2.9 into 10 power minus 4 CB. HF is 50 for CE, minus 51 for CC, minus 0.98 for CB. H naught is 25 microamperes per volt for CE, 25 microamperes per volt for CC, 0.49 microamperes per volt in case of CB. Conversion of H parameters. We have seen in the previous slide that parameters assume different values for different configurations. They are different, but there exists some relation between them. Those relations are given here. CC parameters in terms of CA parameters. Once CE parameters are available, CC parameters can be obtained using these relations. HIC is equal to HIE, HRC is equal to 1, HFC is equal to minus 1 plus HFE, HOC is equal to HOE. And CB parameters in terms of CE parameter. HIB is HIE over 1 plus HFE, HRB is HIE, HOE over 1 plus HFE minus HRE. HFB is equal to minus HFE over 1 plus HFE. H0B is equal to H0E over 1 plus HFE. CE parameters in terms of CB parameter. HIE is equal to HIB over 1 plus HFB. HRE equal to HIB H0B over 1 plus HFB minus HRB. HFE is equal to minus HFB by 1 plus HFB. H0E is equal to H0B by 1 plus HFB. Before going further, one point is required to be mentioned here. When we purchase a transistor, along with the transistor, a data sheet also comes to us. In the data sheet, a lot of information pertaining to the transistor is given. In that information, H parameter values are given. H parameter values for CE configuration are only given, not CC or CB. Now, if we want to use the transistor in CC or CB, then we need to know the H parameters of the transistor in that particular configuration. If we want a transistor in CC configuration, then we need to know H parameters for CC configuration, but they are not given in the data sheet. Only CE parameters are given. So these relations now become handy. HIE is available, given by the manufacturer. HFE is given, H0 is given. From the given values, available values, one can find HIC, HFC, HRC, H0C. Same is the case with common base usage of transistor 2. A few points regarding H parameters. As these are dimensionally alike, they are called hybrid. or parameters in short. They are convenient to use in circuit analysis and design. As already mentioned, analysis can be done only when the circuit is linear one, when the circuit is with linear elements. Then only one can be able to use laws which are meant for linear circuits like Ohm's law, Kirchhoff's law, Norton's theorem, Thevenin theorem, etc. etc. Now, as it is circuits with electronic components, nonlinear components, they are not amenable for analysis. Once those devices are replaced by equivalent circuits which are linear, the total circuit becomes linear, and one can use all those laws and analyze, and also if necessary one can design. So equivalent circuits are highly useful and essential too. They can represent the BJT at low frequencies. This point is specific to H parameters. H parameters are low frequency equivalent circuit parameters, and for small signal amplitudes only. So H parameters are basically low frequency and small signal equivalent circuit parameters. They are easily measured by experiments and can also be obtained from the transistor static characteristic curves. If input and output characteristics of a particular connection are given, the parameters can be determined graphically. Limitations: valid only for small signal amplitudes less than 26 millivolts. Valid only for low frequency. Dependent on operating point, frequency, temperature, vary with aging. Values of parameters are given, but they are not fixed. They vary with operating point, they vary with frequency, they vary with temperature, they vary with aging, and they are valid only at low frequencies. They are valid only at small signal amplitudes. All these are limitations. Now we demonstrate, we illustrate the utility of hybrid parameters in the analysis of BJT amplifier. Here is shown a circuit. Notice this circuit is valid for any configuration. It is valid for common emitter configuration. In such case, HI becomes HIE, HR becomes HRE, HF becomes HFE, H0 becomes H0E. It is valid for common base 2, common collector 2. In case of common base, HI becomes HIB. Similarly, other parameters. In case of other configuration, same changes takes place. So this is most general circuit. It is valid for any one of the three possible configurations for BJT amplifier. Vs is the source, Rs is source resistance, ZL is load, IL is load current, V2 is output voltage, V1 is input voltage, I1 is input current, I2 is output current. Now, if we want current gain is denoted by AI. Current gain is by definition load current by input current. Here is IL load current, here is I1 input current. Because IL equal to minus I2, therefore by definition it is minus I2 by I1. Now using circuit theory laws, principles, theorems, one can determine this ratio. It is not a difficult thing. Similarly, AIS. AIS means current gain when source is taken into account. By definition, it is minus I2 by IS. It is equal to minus I2 by I1, I1 by IS. It is equal to AI by I1 by IS. Similarly, ZI, input impedance. By definition, it is V1 by I1. AB is V2 by V1. ABS is V2 by VS. V2 by V1, V1 by VS, which is equal to AB, V1 by VS. Output admittance Y0 is I2 by V2 with VS equal to 0. and RL tending to infinity. So these are important aspects pertaining to amplifiers. Current gain when source is taken into consideration, input impedance, voltage gain when source is taken into consideration, output admittance. Now, using circuit theory principles and the circuit equivalent circuit, one can determine them. Before going further, one point is to be mentioned regarding the importance of equivalent circuit. As the equivalent circuit is a linear one, this is linear circuit. We are able to use circuit theory laws and able to determine these ratios, determine gains and impedances. The credit goes to equivalent circuit. If transistor is there as it is in the circuit, we cannot do anything. Reason is it is non-linear. We cannot use the laws that are applicable for linear circuits. Now, in the previous slide, definitions of current gain, voltage gain, impedances are given, and expressions for the gains and impedances can be found. It is not a difficult process. Using simple circuit theory laws like Ohm's law, etc., one can find out. Zi input impedance is equal to Hi minus Hf Hr by H naught YL. Ai is equal to minus Hf by 1 plus H naught ZL. Ai is equal to Ai Rs by Rs plus Zi. Y naught is equal to H naught minus Hf Hr by Hi plus Rs. Ab is equal to Ai ZL by Zi. ABS is equal to AB Zi by Rs plus Zi. Notice these are common expressions, general expressions valid for any configuration. If we want values for C, then Hi has to be replaced by HIE. HF has to be replaced by HFE. HR has to be replaced by HRE. H0 has to be replaced by H0E. Similarly, for other configurations. Now, here is provided some information regarding BJT amplifiers. Current gain, voltage gain, input resistance, output resistance. For CE, it is a high. Current gain and voltage gain both are high. Input resistance is medium. Output resistance is also medium to high. In case of CC, current gain is high, voltage gain is low, input resistance is high, output resistance is low. For CB, current gain is low, voltage gain is high, input resistance is low, output resistance is high. Typical values are also given here. These values are obtained by substituting H parameter values in the expressions that are shown in the previous slide for gains and impedances. Now, a few points regarding a simplified equivalent circuit. Here is shown a simplified equivalent circuit for BJT. It is simplified because in actual circuit there are four elements: one resistance, one conductance, and two sources. But here in this circuit, only two elements, one resistance and one source. So complexity has got reduced to half. Now, this circuit can be used in the analysis of amplifier circuits, BJT amplifier circuits, to find gains and impedances. When it is a CA configuration, the circuit appears like this. When it is a CC configuration, circuit appears like this. When it is CB, circuit appears like this. From this circuit, one can find current gain, voltage gain, input resistance, output resistance, etc. Some points regarding simplified equivalent circuit. Only two of four H parameters, HIE and HFE, are sufficient for analysis of low frequency transistor circuits, provided the load resistance R is no larger than 0.1 by H naught E. Same equivalent circuit can be used to analyze any configuration by grounding the appropriate node. Hence, values of only two parameters are sufficient to approximate the BJT in all its three configurations. So, one circuit is sufficient, can be used with any one of the configurations. It is able to give only approximate results. Even exact H parameter equivalent circuit also gives not exact results, but this fellow gives much more inexact results, much more approximate results. However, the error in current gain, input impedance, voltage gain, and R naught with the simplified model is less than 10%, provided RL H naught E is less than or equal to 0.1. The approximate circuit is always valid when CA transistors are operated in cascade. Some points regarding simplified equivalent circuit. Here are shown expressions for gains and impedances when approximate relations are used for analyzing BJT amplifier. Current gain. For CE it is minus HFE. For CE with RE it is minus HFE. For CC it is 1 plus HFE. CB it is minus HFB, which is equal to HFE by 1 plus HFE. Similarly, input resistance expressions are given. Voltage gain expressions are given. Output resistance with load are also given here. With this, we come to an end of the session. In this session, H parameters are introduced and their importance, their limitations in the analysis of BJT amplifier circuits are described and discussed. Hope this session is useful to you. We meet again in another session, a new topic soon.